Welcome to this first video on biological molecules. A really good starting point for an understanding of biological molecules is to remember that organisms, as much as we're cellular, we're really just a big combination of chemicals. So it's important to start looking at chemistry and chemicals and how that relates to an organism. One of the things we have to clarify at the beginning is organic versus inorganic. And what we're going to realize in the next video is a very clear distinction of organic molecules versus inorganic molecules. But what I want to mention in this video is that what we have here is organic molecules tend to be covalently bonded together. All chemical systems have got chemical bonds in them. These things, inorganics, are ionically bonded. And somewhere in the middle, there's a third variation of this, and there's a polar covalent bond. Now, to understand this is really important right now. Let me use an example and see if I can help clarify it. So if we're looking at a situation here, we might have a hydrogen atom, and hydrogen's got one electron, and it shares that electron with another hydrogen atom, so we have H2. That's a covalent bond. Both atoms are exactly the same size, and they each have one electron, and that's shared. That's one way of drawing it using a dot diagram. That's a chemical formula, and we could even use a stick diagram like this, where we have the chemical bond, the covalent bond, is represented by a little line. That gets converted to that. That's a covalent bond, and we have hydrogen, we've got all the diatomic molecules, and as we're going to find out, we've got huge, huge molecules, lots of covalent bonding. The flip side of that is ionic bonding, and for an example there, maybe I'll pick sodium and chlorine. Well, chlorine has 7 electrons in its outer shell, and I'll just draw electrons here, in its electrons here, and sodium has 1. The affinity of chlorine for that electron is that it actually uses that electron exclusively. Sodium, what they say, it actually donates the electron to chlorine. So sodium is left with a full shell in its inner shell. This was in the outermost shell, but now the second orbital is full because it has its 8 electrons. This one has 8 electrons, so we have NaCl, but what's really going on is Na has donated that electron. It's got a positive charge, chlorine has got a negative charge, and the difference in charges hold them together as a molecule. So that's the other extreme of that. So that's, a general science type chemistry topic, and I don't want to get into that any deeper here, but you should have an understanding of that. But what we have somewhere in the middle is polar covalent. Now, this is one extreme, here's the other extreme. So what happens if it's not quite that extreme? And the example I want to use there is water. I've already said that organisms are a lot of water. Water is really important. Let's have a look at it. Here's oxygen. Oxygen has 6 electrons in its valence shell. Water is H2O, of course. Hydrogen, I'll put X's for hydrogen. That's its electron there. And I'll put another one here. That's its electron. So you can see what's happening is these electrons are paired up. There's 2 in that shell, and the stable numbers are 2 and then 8. So we've got a full shell for hydrogen here, full shell for hydrogen here, because they are sharing these electrons. And then oxygen has 1, 2, 3, 4, 5, 6, 7, 8 all the way around. So oxygen has 8 electrons, or the use of 8 electrons as well. So that works. This is a covalent molecule, except oxygen's a way bigger than hydrogen. Oxygen has 8 neutrons in its nucleus, or 8 protons in its nucleus. Hydrogen only has 1 neutron or proton in its nucleus. So this has a much more positive charge in here. What happens really is not this so much. I'll just draw the stick version. So we have oxygen like this. There's the bond to hydrogen. There's the bond to hydrogen. And this bond, of course, is a sharing of 2 electrons. We've got hydrogen here. But because of what we say, the affinity of oxygen's nucleus for the electrons, because this is so positive compared to this has a plus 8 nature to it, there's only a plus 1 nature, is these electrons wind up getting drawn that way. So they're not shared equally. The electrons spend way more time around oxygen than they do around the hydrogen. It satisfies the thing chemically because the numbers work out, but this is what it's more like. So the oxygen part of this thing has the use of the electrons most of the time. What that does though is it means that the hydrogen down here, without that electron, or without the electrons, without both of them, is sort of positively charged. We say it has a positive dipole, and it's written like that. That's the small Greek letter D, positive dipole. This one has a positive dipole as well, small Greek letter D. So there's a positive nature here. Of course, there's a negative nature around the oxygen because it has the use of more electrons. It has 8 protons. It has 8 electrons, but in nature, in respect to the other thing, the rest of the molecule, this has a negative nature. It has to balance that. That's what water is like as a molecule. It's not exactly a straight line. It's not exactly 90 degrees. This angle in here, because there's electrons up here, it's pushing this thing down. This angle is really, it's a 104.6 degrees. So if you're drawing these things, it's drawn roughly about that angle, the way I've illustrated it there. Very important. This is really important to understand how water is as a molecule, and it's fundamental to life. This allows the water to have a set of characteristics which life on Earth depend on. That's what I'd like to get to. So let me take this away. Do you think you could ever get one water molecule? You can get a drop. Imagine how many water molecules are in a drop of water. The answer is millions. There's a ton of them. So you get a water molecule like this: oxygen, hydrogen, hydrogen. And you have the dipoles, the positive dipole here, negative dipole there, positive dipole there, and you throw in another water molecule. What do you think it's going to do? Opposites attract. So the other water molecule is going to come in here and orient itself so that it may orient itself so it looks like that, or in that position. Of course, we've got the positive dipole on the hydrogen here, and here we've got the negative dipole there. This attraction here, because these dipoles are opposite attraction, this is sort of held together by a weak bond, an association between opposite dipoles. Opposites attract. This is called a hydrogen bond. And it goes on, because if you think about it, you don't just get 2 atoms of water, or 2 molecules of water. You get millions of molecules of water. So there's another molecule of water sitting over here. And there'd be another one sitting over here. And there'd be another one sitting over here. And it could be another one sitting over here. And every one of them, I won't draw all the dipoles in here, but every one of them is sort of held into position by these hydrogen bonds, the attraction between opposite dipoles. That's really critical, because what it does, it means that water is cohesive. Water molecules are cohesive, not adhesive. Adhesive means something adheres to another substance. Like tape adheres to a wall, adhesive tape. Cohesive means it sticks to itself. So water molecules are sticking to itself here. So I'm just going to make a list here of characteristics of water molecules. And that's the first one. Characteristics of water molecules. The first one is cohesive. Means they stick to themselves. The reason they stick to themselves is because of attraction between opposite dipoles. What this does for water is it gives it some particular characteristics. Like overfilling a glass of water. I'm sure everybody's done this. You take a glass of water, I'll flip over here. Here's a glass. And you put water in it, and you know, you can actually take the water and fill it, drop, 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 right over the top. And the water can actually overfill the glass. And if you put one drop too much in, it'll drip down, of course. But if you take a look right at the side of it, the water can just bulge over the top like that. And the reason it does that is because these ones are being held onto those ones. The water molecules are cohesive. They're being held together like that. So that's one of the features of water. It's cohesive. And the advantage of that, in addition to surface tension, that's surface tension like this. It provides surface tension. That's important for little water striders, the little bugs that crawl along the top of the water. Sometimes in the water puddles you'll see the little bugs are actually walking on the water. And they're walking on the water because they're not heavy enough to break through the surface of the water molecules because they're being held together by this hydrogen bonding, providing this surface tension. Another thing that cohesion does for water molecules is it allows capillary action. And let me see what I can do to illustrate capillary action. I'm going to leave my hydrogen bonded molecules right there, but if we take a look and you've done this one too. As an elementary school student, you've probably taken a glass or a container and you've put liquid water in here and you maybe put some food dye in here, so maybe it's red, and you put a stalk of celery in it. I should use green for celery, but you put a stalk of celery in it and you leave it, and pretty soon the top of the celery, you see the red moving up the celery. What moved it up? Well, it's capillary action for the most part because it's being drawn up here. It allows it to travel in tubes. That's what capillary action is. There's a little bit more going on in this one, but capillary action allows the water to travel through tubes, and that's in their bodies, through our bloodstream. It's the same sort of thing as that, so that's really, really important. Another characteristic of water is that it's a very good solvent. Things dissolve in it. So we go back, I just mentioned blood. Blood is mostly water, 92% water. Well, there's stuff floating around in our blood. There's things dissolved in our blood. And like ions, they're fine, they're mixed in there, because ions, positive ions, negative ions, you can imagine positive ions, they float along in here just fine because of the positive and negative natures of the water molecule. There are things that don't mix in blood very well, so we have things which are hydrophilic. Those are the things that like water. Philic, hydro is the water. But you also have hydrophobic substances. So, for example, fat molecules or cholesterol molecules, they don't go through the blood very well. So even if you take, I can go back and use this space again. You take this glass of water, there's the water, we put the water in the bottom, and you can drip a little layer of oil on top. Well, the oil is going to sit like this. And even if you shake it, you stir it, you mix it all up, you get all the little bubbles in here like salad dressing, and eventually if you leave it long enough, it'll form a layer on top again. Because it's hydrophobic. The reason it's hydrophobic is oil is not polar. It doesn't have dipoles. It doesn't mix that way. That's really important in organisms. In our bodies we have polar and non-polar molecules, and that allows for a separation in substances in our body. We'll have to get into that later on. So water is a very good solvent. Difference between hydrophobic and hydrophilic is important to know. Water hating and water liking. A third characteristic of water is that it has a high specific heat capacity. Now that is a lot to say. High specific heat capacity, we just call it high heat capacity. What it means, quite simply, is that it takes a lot of energy to change the temperature of water. I mean, sure, you think, oh yeah, we put it on the stove, we heat it up. Yeah, but that's a lot of energy. That's a lot of energy. We look at a body of water in the summer, so you have a lake in the summer, and the sun's beating down on it, and it takes a lot of sunlight to change the temperature of that water. And in the fall, it doesn't cool down as fast as the air does, that sort of thing. So high specific heat capacity. That's good for us. It gives us a body temperature. Because at 37 degrees, which is roughly normal body temperature, it takes a lot of energy to make us 38 degrees. Or it takes a lot of cold to cool us down, so we're suffering from hypothermia or a cold body temperature, maybe 35 degrees. That's a little bit hypothermic for me. So, but it takes a lot of energy. You can walk around in the sun all day long, your body temperature is still 37 degrees, or maybe a little bit elevated, but not much. So it has a high specific heat capacity. The reason it does is because these bonds are flexible. They're very weak bonds. They're not a strong bond. So if this bond, they're weak bonds. If this bond breaks, this molecule can twist around and attach to another one over here. Or if this one breaks, this molecule can, it floats around and it attaches over here, for example. But it's always hydrogen bonded together. The warmer it gets, the more these bonds shift and the more they break. The colder it gets, the more these bonds stick together. They get a little bit more rigid. But it takes a lot of energy to actually change the temperature of the water because, as a system, it's very flexible, very adaptable that way. Another feature of water that's important to organisms. It's a lubricant. Now, an example of this, a really good example of that is, go get a bag of crackers and eat them without taking a drink of water. It doesn't take very long to get a dry mouth because you produce saliva, you swallow, there goes one cracker, it's a lubricant. We have water in our joints, our systems inside. It's wet, sure, if you cut yourself open, or if someone cuts themselves open, you see blood, but inside the joints, there's fluid, and it's water. It's a lubricant. It allows things to move properly and through tubes and so on like that. Another feature of water that's really important to organisms, not all organisms, but some organisms, is the fact, that's a 5, the fact that it's transparent. And I'm thinking in terms of algae. Algae's in the water. Some algae, like red algae, can be meters deep in the water because the water is fairly transparent. The sunlight can penetrate and it can conduct photosynthesis even though it's not in sunlight, direct sunlight at all. So that's really important for some organisms anyway. And another one is that it's neutral. It's not acidic, it's not basic, it's right in the middle, it's neutral. And So before we go back and dissect this neutral one and take a closer look at it, I just want to go back up to this one, something I neglected to say with the high specific heat capacity. This is the one that moderates climates. You recognize that areas that are at the coast don't have as severe temperature fluctuations as areas that may be inland. So if you're by a lake, the lake has a moderating effect on the environment around it, and so on and so forth. So it's really important to recognize the nature of water molecules in the system. Characteristics of water, I like to identify it in terms of 6 characteristics. Of these, some of them are really important in us as organisms. This one is really important for humans. This one is really important for humans. This one's really important for humans in terms of body temperature. We need to be able to lubricate as we swallow our food and our joints and so on. The fact that it's transparent isn't so critical for us as humans, but it's certainly important for others. This is important for humans. So characteristics of water that are important to humans, or if you had to look at it in terms of important to life on Earth in general, they're all important. This topic, we have to elaborate this topic, this neutral business. And I can get rid of this picture now, I think. Water's neutral. It's not acidic or basic. And here's why. Here's our molecule of water. Water will dissociate. Dissociate means that it comes apart. It forms ions. So we get hydrogen ions and hydroxide ions. Could put the little AQ here to represent their aqueous. Acids have an abundance of hydrogen ions. Bases have an abundance, in a simple sense, bases have an abundance of hydroxides. Water has both in equal numbers. It's neutral. The amount of hydrogen ions and the amount of hydroxide ions in water is about 1 × 10⁻⁷ per liter. That's not very many. It does dissociate, but that's how many dissociate. So we're just looking at the hydrogen itself. We could look at the hydrogen ion concentration, which would be written that way if we're taking chemistry, is equal to 1 × 10⁻⁷ per liter. Ions per liter. This relationship here allows me to define pH. pH. pH of water is 7. 7 is neutral. Now, I'm sure that you can see where the 7 comes from. Right there. The pH mathematically is equal to the negative exponent of the hydrogen ion concentration. Right? So the negative exponent of the hydrogen ion concentration. For water, that -7 gives us a pH of 7. 7 is defined as being neutral. And if we go and look at things which are less than 7, a pH of less than 7, these are our acids. If we have something which has a pH of more than 7, it's alkaline or a base. Alkaline and basic mean the same thing. So let's look at some examples. I've mentioned blood several times in this video already. Blood's pH, if I say this is 7, right there, pH of 7, blood is around 7.3. Blood's basic. Just a little bit basic. But what it means is that there's less than, there's more than this number, 1 times 10 to the negative 7 hydrogen ions in a liter of blood. If we look at something that else you would recognize, perhaps a cup of black coffee. Black coffee without cream and sugar, all that stuff in it. 5. Coffee is slightly acidic. It's not really acidic. I mean, you can drink coffee. Sometimes coffee is a little bit more bitter and you get, okay, it's not quite the same taste, that sort of thing. You go down further, vinegar. You don't want to drink vinegar. Oh, you can drink a little bit of vinegar, it's not going to hurt you, but we're talking about a pH of 3. That's an acid. Vinegar is acetic acid. We want to go a little bit further down here. We can pick on lemon juice. It's even tartar. You don't want to, lemon juice, you don't want to eat that at all. We're talking a pH of around 2. Hydrochloric acid, stomach acid, gastric acid, pH of around 1. You're not going to drink that. That's going to hurt you badly. So those are acids. What that means is that there's a lot of hydrogen ions floating around in these things. The pH is less than 7, but that's the negative logarithm. So these have got lots of, the pH is less than 7, but this means that they have a high hydrogen ion concentration because it's a negative logarithm. It just seems like it's backwards, but that's the way they defined it in the first place. What about on that side? Well, we get substances like bleach. You don't want to drink bleach. Maybe 12, pH of 12, it's going to hurt you badly. Ammonia, not quite so alkaline, it's basic, those sorts of eggs. People eat eggs all the time. Eggs have got a pH of around 8. So there we have this sort of stuff. So looking at this, these things in relation to our body, I mean, our body is very close to neutral, blood's around 7.3, it could be 7. Depending whether you're in muscle tissue or in the lung tissue, it's a little bit of variation there. You can eat this, it's not going to hurt you. If you go up into here, that's going to hurt you. You can drink that, it's not going to hurt you. You don't want to do that. You certainly don't want to do that. You get this big range like that. And I think that sort of wraps things up a little bit with one exception. Because we do eat some of these things. We do eat things that have got a tart flavor to them, something brought about by the acids. And our body has a way to adjust all that stuff. I did mention one example back here. If you caught it, stomach acid, gastric acid, pH of about 1. Blood about 7. So there has to be some way to keep that separation. We have to be able to adjust that. I mentioned something here, blood, depending on whether you're in the muscle tissue or lung tissue, 7.3, maybe high 7.35, 7.38 maybe in lung tissue, close to 7.4. We have things in our body called buffers. And a buffer is something that will either accept or donate ions to prevent a pH change. That's what buffers do. And the one that's very common in our body is bicarbonate. Bicarbonate ions. And if this thing here, this bicarbonate ion, was to accept a hydrogen ion, if you added another hydrogen ion onto here, so this -1 would become no charge here, you'd have H2CO3. Oops, that's not CO3. H2CO3. H2CO3. Carbonic acid. And it dissociates. It doesn't hurt you. It's all right. The bicarbonate ions can also donate a hydrogen, so you can actually add a hydrogen to a system. So bicarbonate ions, very important in our body. It's called an amphoteric buffer because it can do both. It can donate and accept. So it's an amphoteric buffer. Amphoteric. So I think that gives us a really good starting point. Our body's close to neutral in terms of pH. We know we've got an organic system. We know we've got water, which is really important. We know there's all sorts of characteristics of water, and those topics come up throughout the whole video series and throughout all of biology. Thanks for listening. And if you'd like to hear more, don't forget to subscribe to my channel. You see the little green gecko in a circle right about there. Thank you.